Our senior design project, the biomedical optical sensing system, is a pulse oximeter. Now, what makes it different than a commercial pulse oximeter? Here's one, but notice that it uses transmission technology so that light has to transfer from the top to the bottom through your skin, which means that it limits that you can only detect heart rate and oxygen through extremities such as your finger or ear. Here we redesigned it using reflectance technology. Therefore, you can not only detect it using your extremities, but you can also put it on your wrists, your chest, and anywhere else that can reflect light off your skin. Furthermore, it's wireless, so it transfers data through Bluetooth to your Android app phone, which through an Android app can display your heart rate and your blood oxygenation saturation levels immediately on your screen. Alongside with that, the device is meant to be long-term wearable, so it's going to last for a long time, and you can wear it and keep track of your data all day.
While reflectance sensing is something that sets our product apart from typical pulse oximeters which just use transmission, it brought its own design challenges. One of the issues with reflectance is that you have to capture light that's backscattered instead of transmitted directly through the finger. Usually it's harder to get as good of a signal from that, meaning one with a high amplitude that makes it easy to read on an ADC. One of the things we did to help solve that problem was by having 3 photodetectors around our light sources. By doing this, we had 3 chances to catch all of the light that was reflected back from your pulse in your finger or wrist or from wherever. The other reason we did this was because when our preferred measuring spot was the wrist, and it can be hard to find a good spot on the wrist compared to your finger to get a good pulse reading. Again, by having 3 sensors in a half circle around the light sources, it gives us 3 times the chance to find that spot for a good reading without moving around too much. A big part of our design was that it was wearable. So like I had already previously talked about, size and using reflectance technology so that we can measure from the wrist was important. Another thing was making a smartphone app for receiving the data and calculating your heart rate and SpO2 value. This was really important because many people have smartphones and it's part of a mobile experience. You can't use a computer and carry it around with you all the time and still have it be as easy. So learning how to make a smartphone app for this that was easy to use and simple was extremely important for our project. Another part of being wearable and continuously wearable is the device needs to be on for a long time. If you have to recharge it every 3 hours, it's no good. So making our device very low power, particularly lasting at least 24 hours on one full charge, was also created a few challenges. Many of the parts that we chose were extremely low power. We calculated out low currents, and many of the ICs, the digital ICs we chose, had various sleep states, low power states that we could use to help extend the lifespan of our device, making it something that someone actually could continuously wear for some time.
Here's our block diagram. Starting from our left, we have 3 different user inputs: USB in, user input, and user test site. Our power block supplies voltage of 3.3 volts to sensor block, ADC, microcontroller, and wireless communication. The idea for all these blocks is you have the light being detected by the sensor, and then the sensor will have an analog output to your ADC. The analog will be converted into a digital signal through that block into our microcontroller. After that, our microcontroller will send the signal to wireless communication, which will be transferred into a high frequency 2.4 gigahertz Bluetooth signal. That Bluetooth signal will be sent to our display device, our Android phone. We have 2 different code blocks: microcontroller code and display device code. Microcontroller code provides all the necessary procedures to operate our device. That includes our timing for the lights, as well as transferring our signal through the ADC into the wireless communication. Our display device code has the processing included to take the data and then display it into a graphable format for user to see. This graphical user data is expressed as our output visualized user data. Finally, we have enclosure block, which is our 3D printed box with our wristband, and that is affected by our environment in.
So here we have the biomedical optical sensing system. As you can see, the board tucks nicely into the case that was 3D printed and designed in SolidWorks. It's hooked up with an elastic wristband so that it can fit well around a wrist of any size. And this is going to be the demo. First step is to put it on, which involves sliding it on your wrist, then tightening the elastic strap quite a bit because it's necessary to be very flush against your skin to get a good measurement from the wrist. You just tuck the battery underneath the wristband. Now it's ready to connect, so we're going to move over to the smartphone app. We'll load here. And going to connect. Pops up a screen of devices to connect to. Sometimes it fails to connect, obviously during the live demo, so try to connect again. And as you can see, this time it connected. So now the device has been connected and we've started collecting data. What the start button does is it will send a command to the microcontroller which will tell it to start collecting data and send the data back to the smartphone app, at which point it reads in each data point individually and it will graph it in real time so you can see the pulse as it is happening. Every time the window is full, it will clear the window and then calculate out heart rate and SpO2 from that last set of data. And additionally, there's a smoothing algorithm built in that will attempt to smooth the data out every quarter of a window. And it's just a simple averaging filter, so it takes a few points around the current data point and averages them together to smooth it out. And one of the key things about our device that we wanted is a continuous monitoring system. You want to be able to see data over time. And so one thing that we implemented was a log screen, which shows your last 20 data points. And at this point it just logs every time the window fills, but it's something that can be adjusted depending on what time frame you want to look at, every half hour, every hour, 2 hours, whatever. So that concludes our device test.
Guys, pay attention.
The key to success in senior design is planning ahead. Because you don't want block tests to come around winter term and have to pull 3 all-nighters. And then pull 3 more all-nighters for final checkoff. And then pull 3 more all-nighters for expo.
Second tip is to find a good mentor. Having a good mentor to consolidate your design with over fall term will be highly beneficial in winter term as you implement your design.
Third tip is to use some sort of file sharing like Dropbox and Google Documents. We found it really helpful for editing documents at the same time and making sure that everybody was up to date with our files.
Duck face.
Be a winner.
Vote Ron Paul for president.